Hello everyone. Let's get started. Today I'm going to cover OpenVINO for audio and speech data. First of all, please let me know in the chat if you can see my screen and you can hear me clearly.
We can.
Okay, thank you. Let's get started. The session is already being recorded, so the people who cannot make it, they will find it later. The topics I will cover today is I will talk about the classical and modern approach for speech recognition. Then I will talk about the speech data preprocessing. I will talk about convolutional neural network for speech detection, just a little overview, and then how to get started. How can you actually get started with doing some speech related project? Then training with your custom data. There is a little demo for you, which some of our fellow members have made, and they're kind enough to show this demo for you guys. And then we will do some project idea brainstorming, which will be fun, I guess. Okay, so now speech is everywhere, we know. With the rapid development of mobile devices, speech-related technologies are becoming increasingly popular. Now, we have Google search by voice on our Android phones. We have personal assistants such as Google Now, Apple's Siri, Cortana, Amazon's Alexa, etc. Let's see a very interesting speech-related product, which I found really interesting. Let's see. I think some of you have already have seen this, but let's see. Okay, so as you can see that it was pretty interesting that using voice and your speech, you can make Amazon do a lot of things for you. So that's why this topic is actually very interesting to me. So let's talk about the classical approach for speech recognition, because speech recognition is not new at all. It's quite old actually, but recently it got more attention because of the rise of neural network. Because using neural network gives are giving better performance as compared to the classical approaches. So what happens in a classical approach is we have this audio, we have the signals, right? Then we pass it to the speech preprocessing step, and some classical signal processing has been applied. Then we pass it to the features, and as you can see, so basically the core idea is that we have predefined set of features like phonemes, their uh, you know uh, yeah, basically phonemes, syllables, etc., which are basically n-gram models. If any of you have worked in NLP or natural language processing, you will know that in text language also we have n-gram models where we actually separate the words or by their phonemes, by characters, etc. So same idea has been applied in speech as well, where we have a bank of features, and when we get a new speech or new audio, we separated into, during pre-processing step, we separated into multiple phonemes or multiple features, and then we compare to the feature bank, and and we take the one which has the highest probability for that particular feature. So that's how it has been done for a long time. But now we have some modern approaches. One of them is connectionist temporal classification, which is highly used by Baidu and Google. Then we have sequence to sequence models, or RNN or LSTM. Then we have convolutional neural networks, CNN. So because our course is mostly covered CNN and computer vision tasks, so I will focus my webinar as well on this part only. I will not cover the sequential models and CTC. So I think all of you, by this, if you have started the course, you will have a little bit understanding of convolutional neural network. But still, so that we are all are in the same page, I will give you a little overview. So basically, it has multiple set of convolutional layers stacked together, right? And it can have as many layers as we want. The more the layers, the deeper the network. The for image classification or for computer vision, which our course is about, so what we do, we pass a two-dimensional input image to the layers, and each layer collects some features. So the preliminary layers collect more low-level features, the intermediate one collects more mid-level features, and the final ones actually collect more high level features, which is basically the combination of all the other previous layers. And finally, those features are passed to the classifier, and then using the result, you can do a lot of things, right? Now, for image, what we do is we convert this image to a 2D matrix of numerical numbers from 0 to 255. So that's how we do it for images. But for speech, how do we do? Because for speech are basically signals. Here, if we can see, there are many examples of speeches like acoustic guitar, bass drum, cello, etc. And if we plot it in a 2D graph, then it has time. In the x-axis, it has time in seconds, and the y-axis, it has the amplitude. So basically, that's how we can represent speech as signals. Now, to pass this information to a neural network, we need to do some pre-processing. First is turning the sounds into bits. So as example, in the top, if you can see, there is one speech. This is a waveform of a speech. And if we zoom in a little portion, as defined by the red box, we can see that it's a sine wave. It's a complete wave in that portion, right? And using that sine wave, we can actually get some bits, get some numbers. And how do we get the numbers? It's basically the height of the signal at equally spaced numbers. So if we take the heights in the next picture, if you see, if we take the heights of different equally spaced time interval, then we will get those numbers. Now, next step is to build some spectrums. So yeah, okay, building spectrograms, sorry. So imagine you have a recording of someone playing a C major chord on a piano. Then that sound is the combination of three musical notes, say C, E, and G. So all are mixed together into one complex sound. Now we want to break apart that complex sound into individual notes to discover that they are C, E, and G. So this is the idea. So how we do this? We do this using a mathematical operation called Fourier transform. And it breaks apart the complex sound wave into simple sound waves that make it up. So once we have those individual sound waves, we add up how much energy is contained in each one. So the end result is a score of how important each frequency range is from low to high. And each number below, as we see, represents how much energy is in each 50 hertz band of the previous 20 millisecond video clip. So the previous example, this one is actually a 20 millisecond audio. So if we zoom into the 50 hertz portion, we will see this full wave. And then based on that, if we plot if we get the energy for that particular portion, we will get these values. Now, if we plot the values, we will see like a color, right? And we can see that this is a spectrogram of one little portion of the 20 millisecond of audio, or one little chunk. So if we stack multiple of them, we sample it on a lot of samples. So 20 millisecond, as example here, it's 20 millisecond times 320 samples per window. So if we stack them together, we will see this, we will get a two-dimensional spectrogram or image, which is similar to the images we use for our computer vision task. Now, previous example, going back to previous example, so the acoustic guitar and all the examples, if they are converted to spectrogram, they will look like this. We have a lot of libraries to convert audios to spectrograms or audios to waveforms. They're pretty straightforward. One is Python LIBROSA library. So using that library, you can easily get the waveform of one audio. Then you can also get the space. So if you just use librosa.display.space spec show, that's it, and you will get the spectrogram of the audio. Now, once we have the 2D spectrogram, we can easily use it in our CNN model just the way we do it for our computer vision task. And the rest of the parts are same as well, because now we have a 2D array. Now, how to get started? So OpenVINO Toolkit supports these following frameworks as of now: Caffe, MXNet, TensorFlow, Caldi, and ONX. So in TensorFlow, simple audio recognition, if there is it's actually very good starting point for the beginners. So let me just go through it quickly. So simple audio recognition, it basically uses speech command data set, and which consists of over 100,000 wave audio files of people saying 30 different words. It's collected by Google. And using that actually, and using TensorFlow, you can very easily train your model. And in TensorBoard, you can see the result, the training loss and testing loss, you can see it. Then you can also run the model in Android app. It's also pretty straightforward. And these are some detailed explanation of it. Now, next we have Caldi. So Caldi is also another open source toolkit for speech related data. This is especially for speech related data. So, and it also has a very good documentation. So yeah, this is called Awesome Caldi, and it has all the good resources for beginners. So how to start with Caldi and recognition stuff. And yeah. Start. So now if you want to, so you can do it using the pre-trained models in TensorFlow and Caldi. But what if you want to do your custom training on your custom models? So obviously you can use one of the pre-trained models to start with, which is called speech command data set. And on top of that, you can add your own data. Now, to train your own data, you should make sure that you have at least several hundred recordings of each sound you would like to recognize, and arrange them into folders by class. So it's very obvious, but the thing is, you need a lot of data, unlike images, because in pre-trained models, I think hundreds of more images you can add on the top of the pre-trained model and you can make it work. But for speech, because it's more difficult task, you need a lot of data for a simple new class. Now you have to take care of a few other things like unknown class. So you will want the model to indicate when it doesn't recognize the noise, which is not in the training set. So that's why in your training set, you need to add some. So as example, if you want to classify 5 different animal sounds, you need to add a 6th class consisting any other different sounds which doesn't belong to those animal sounds. And this class will tell your model to classify a new sound as unknown class if it's not present in the training set, if it thinks it's not present in the training set. Now we have background noise, because in real world our speech, it's not very uh, one dimensional, because we have a lot of background noises. If you record from another person, the environmental noise and everything comes together. So that's why you need to add some background noise in your training data as well. The background noise will contain minute-long wave files with white noise and recordings of machinery and everyday household activity. It can be anything. So the small snippets of these files are chosen randomly and then mixed at a low volume into clips during training. You can use all your creativity in this. Then silence. So in most cases, the sounds you care about will be intermittent, and so it's important to know when there's no matching sound. So that means in a, because audio data is time, like a continuous data, but whenever, even if a speaker is not speaking, still there are some sounds. It's not completely silent at any time. So that's why we need to add some data set which have some irrelevant noise, which not a speech, but not not a background noise as well, but it's just some irrelevant sound. Then time shifting you can use for your dataset augmentation. It's basically a random offset in time of the training sample data, so that a small part of the start or end is cut off and the opposite section is padded with zeros. So you just randomly cut portion of your input samples and then pad it pad it to both sides as zeros, and then add it as another input audio. So some of the generic problems related to speech and audio are speech recognition, speaker recognition, speaker diarization. That means segment the audio by speakers, individual speakers. Then speech to text, obviously. Then voice control edge devices. Now, so you many of you know these people like Arco, George, Case, Arti, Temitope, Avinash. So a big shout out to them because they are willingly showing a demo. They made this demo for you guys to show in this webinar. So a big thanks to them. So let's see the demo. Actually, they made a speech to emotion recognition system, and they have successfully deployed it in the edge. So this is they have deployed it into the desktop as well as in mobile. So this is the one they deployed in their desktop Linux. So here you can see that they're showing a little test in front of us. Uh, so basically the audio files are converted into spectrograms, as you can see. So they are now passing the spectrograms. Yeah, so you can see the label is surprise, and it's predicting surprise correctly. Then let's see another one. Yeah, so it's supposed to be an angry speech. Okay, it shows neutral. So yeah, I mean, your model can never be 100% accurate. So let's end with a good result. Okay. Okay, I think now it shows angry. All right. So these are the references I have used, which you can use. And now let's do some project idea brainstorming. These are the categories provided by Udacity community for our project showcase. So you can build any of the, build your projects in any of the category or anything else. So if you want, it's a good time for us to do some brainstorming, like what kind of speech related project we can have in art or in cybersecurity or in education, etc. So now the floor is to you guys. Please ask me any questions or anything. Yeah, thank you. Okay, let me. Yeah, let me unmute. Okay.
Hi, Zari.
Hi, hello. Yeah.
Yeah, I'm Lakshmi. I have a question on the speech recognition.
Mhm.
Like for image processing, we'll do a lot of pre-processing. like take Gaussian transformation or Laplacian transform. So similar to that, do we do any processing here? Because you mentioned about adding noise to the speech signals,
Mm-hmm.
but sometimes the problem is the data we have will be with lot of noise and the system may not be able to recognize. So any pre-processing needs to be done on that data to clear the noise and extract what we want, something like that.
Yeah, I think the thing you're talking about, it's noise removal, and it's mostly done using signal processing. So the pre-processing step I showed is basically useful when you want to pass it like your whole data, like after doing all the noise removal and everything, like you have your raw input ready to use. That from that you can use those spectrogram and other stuff to pass it to the neural network. But what you're saying is actually it comes even before that. While you are collecting, like after you collected the data, then you can apply the noise removal, adding some background noise. So it comes even before that. Yeah.
Okay, yes. Thank you, Zari.
Thank you. So anyone have any idea the about some projects in any of the categories? I have unmuted you guys. So John says, would it be possible to build a NN to correct the speech for people with impairments? Yes, yes, absolutely. Absolutely. That's a very good idea actually. Yeah. Which category it falls under? Health or social good, maybe? What about art? Do you have any idea? Because I was thinking also, like what projects can we have in each of the category, but I cannot find anything in art. Do you have anyone have any idea? Speech related to art, maybe music. Mm.
Uh, Hi, Zareen. I think I got some idea on the music part. Like you were talking about having in the one octave, C octave itself, the mixing of C and right.
Hmm. Yeah.
So like that, if you take there are some tunes like suppose there is a famous tune. Uh, just with one line of the tune, we can identify the song or
Hmm.
it is especially in Indian classical music. There are different kind of we call it like ragas. That's the combination of these octaves will give us raga. So, but that will obviously need a lot of like musical data.
Yeah, right. But I think the musical data, first of all, yes, it's a very good idea. And another part is you can like just like search by voice, you can do search by music. I think it's already there in some of the apps. You can like you can just listen to a portion of the song and it will give you the original song, it will search it for you. So yeah, and what you're saying, like the different categories of classical music you can use, of course, but the thing is for classical music you will need the data.
Yeah,
Yeah.
yeah.
Yeah, it's a very good idea actually.
Thank you.
Also, if you cannot find a lot of data, you can do the some synthetic data. You can generate some data, like you record some original classical music data, and based on that you do some augmentation, and you like using some software, some musical software, you can generate new samples, which will be little variation.
Yes, yes, yeah, I get it.
Chetan Verma says we can use it to predict failure of mechanical machine based on it audio signature. Chetan, do you like to give us a detailed explanation, please?
Yeah. So, thanks for the nice first of all. Thanks to you for nice presentation, Jay. Yeah.
Thank you.
So, what like in factory, there are lots of machines which will mechanical machine which runs actually, and they have a wear and tear happens, and when wear and tear happen, their audio signature will change actually. And wear happens gradually actually. So
Okay.
maybe if we can know what is the good machines of audio signature and what is the VM machine when it's wearing tearing, then based on that, I think we may be able to classify uh, failure actually.
Okay. Okay. That's nice to know.
Okay.
So this signature, when it changes, you can get it from a sound or some audio?
Yeah. So sound actually, yeah. I mean, this will be applied only for sound actually. I mean, the way my mechanical machine which makes sounds actually. Like engine is the one, the conventional engine,
Okay,
or
I see.
yeah.
Mhm. Yeah, interesting. Thanks, Chetan.
Yes, I think I
Okay.
would like to add on to what Chetan was mentioning. So, especially when we need a service time for our vehicles.
Mm-hmm.
So, when there is an oil change required, then these vehicles will have a different sound, but
Mm-hmm.
it is definitely not recognized, not very much recognized with the human ears. But if we can have something that will recognize the change of sound in the machine, means that will prompt the driver to take it to the service.
Yeah. Okay. Yeah.
Yeah. I think
Yeah.
yeah. So yeah, what let's say that we can apply it for like predictive maintenance actually. Yeah.
Mm-hmm. Yeah. It will help human, because we sometimes have our headphones on. We are listening to music and
Right.
driving. We may not always care. Yeah. Right. Thank you, Lakshmi and Chetan. Uh, Ohmarkali says maybe this can be used for animal sound communication recognition, like for dolphins. Oh yeah, actually I have read somewhere like there is one professor. She spent 40 years in understanding dolphin language, but still she isn't not successful yet. So yeah, it turns out that understanding dolphin language is not very easy. Do any of you know anything about this or want to add something on this? Yeah, I have unmuted. Oh, okay, so does anyone have any more question? If not, so maybe we can wrap this up. Uh, does anyone like to say anything? Because I think that's it. We will wrap this session. And thank you everyone for joining this webinar and making it successful. Thank you so much. It was my first this kind of webinar in this sitting. I was clumsy, I know. Excuse me for this, but thank you so much for joining. Really appreciate it. All right, guys, bye and enjoy the rest of the study jam.